angle that it forms, right? So now there are various sections. The section which is represented as C1 is from 0 to plus infinity. Then next section C2 is nothing but this plus infinity to minus infinity, but in semicircular form. And third section is from minus infinity to 0, right? So this Nyquist contour or contour in S-plane, which we were denoting as C, that is right half of S-plane. And here the angle theta varies from plus pi by 2 to minus pi by 2. This is plus pi by 2 line, right? So plus 90 up to minus 90. This shows the direction of Nyquist contour. The direction starts from plus pi by 2 and then it ends at minus pi by 2, right? So the direction is clockwise. Here, our assumption about the Nyquist contour is the Nyquist contour is right half of S-plane in a semicircular form, and that too, it has the clockwise direction, right? Now, the next thing that we need to see is what is mapped contour. Okay, so we have right half of S-plane as Nyquist contour, that is contour C. Now we need to find what is CF. So to obtain CF, we need to substitute values of S in f of S. In our case, the f of S is 1 plus GSHS. So after substituting, whatever we get and whatever we plot is nothing but the Nyquist plot, which is basically a polar plot. But by using Nyquist criteria, we are analyzing the stability, and so we call it as Nyquist plot, right? So now three things we have discussed till now is your contour C is nothing but right half of S-plane, okay? And we call that as Nyquist contour. Then we have f of S considered as 1 plus GSHS, okay? And we need to have CF, which is nothing but Nyquist plot that we sketch, okay? So if these three things are clear, then we will proceed. We have contour C in S-plane, which we assume to be right half of S-plane, semicircular area, that will be called as Nyquist contour. F of S is nothing but 1 plus GSHS, and CF, that is mapped contour in f of S-plane, is nothing but our Nyquist plot. Okay, now let us come back to the Nyquist criteria. So now if zeros of 1 plus GSHS present in the right half of S-plane, now Nyquist contour, are 0, then the system is stable. We have always seen that zeros of 1 plus GSHS are nothing but closed loop poles. So if 0 of 1 plus GSHS lies in the right half, system is unstable. But if no 0 of 1 plus GSHS lies in the right half of S-plane, the system will be stable. So as per our mapping theorem, value of Z must be equal to 0. So if you substitute 0, we get the equation as n is equal to minus p, and if this is called as Nyquist stability criteria. So if zeros of 1 plus GSHS are 0, which are encircled by Nyquist contour, that is in the right half of S-plane, the system is stable. Okay, so what we can check is whether Z is equal to n plus p, which is equal to 0. Okay, so if that is satisfied, the system is said to be stable, otherwise the system is unstable. Now, most important part. So what we have learned till now is our f of S is 1 plus GSHS, C is Nyquist contour, and CF is the Nyquist plot that we sketch. Ultimately, we need to count Z, P, and N. And then using Nyquist stability criteria, we should check whether the criteria is getting satisfied. If yes, the system is stable. If no, the system is unstable. Now let us simplify this. Instead of considering 1 plus GSHS as f of S, we can consider GSHS as the function. Okay, GSHS is nothing but open loop transfer function. So instead of considering 1 plus GSHS, even if we consider GSHS, that would be fine, but we get GSHS is equal to -1. So what we have learned in the mapping theorem, that encirclements n around the origin were counted. Okay. Now, if you make this adjustment that convert 1 plus GSHS to, 1 plus GSHS to GSHS, the equation will be GSHS is equal to -1. And now encirclements around the critical point, that is -1 plus J0, will be counted. Okay. So instead of origin, we count the encirclements around the critical point. Only that is the change. So if we change f of s, then instead of calculating encirclements of origin, the encirclements about the critical point should be calculated. So here the diagrammatic representation shows that we have a Nyquist contour, the leftmost diagram. We have the Nyquist contour, right half of S plane. Then we have the middle one, middle diagram, shows 1 plus GSHS encirclements after sketching the Nyquist plot. And rightmost diagram is change from 1 plus GSHS to GSHS. Here the encirclements around the critical point are calculated. Okay. So now till now what we have discussed is, now ultimately what we will do is we will take an OLTF, open loop transfer function. From open loop transfer function, we are trying to comment on the closed loop stability of the system. We have seen that closed loop poles of the system are nothing but zeros of 1 plus GSHS. Okay, so we will try to find out presence of 1 plus GSHS 0 in the right half of S plane. If it is present, the system is unstable. If absent, the system is unstable. Instead of considering 1 plus GSHS as the function, we can consider GSHS as the function f of s, and then we can sketch the Nyquist plot. After sketching the Nyquist plot, we need to calculate encirclements around the critical point, that is equal to n, and then we have to see whether it satisfies the Nyquist criteria as n is equal to minus p. Now please understand, value of z and value of p are known to us when the transfer function is given to us. So when open loop transfer function GSHS is provided to us, then and there only we can calculate, we can see, we can obtain how many zeros and poles are there in the right half of S plane. Okay, and then those value encircled by the Nyquist contour, that means in the right half of S plane. So value of Z and P are known to us, but please understand, we are not commenting on open loop stability, we are commenting on closed loop stability, and so we need to check the encirclements around the critical point, and then we need to substitute in the equation n is equal to Z minus P and check whether n is equal to minus P or not, where Z is equal to 0. If that is satisfied, we will say that the system will be stable. Now there are possibilities. When we consider the contour, Nyquist contour, there are possibilities that there are some poles on the imaginary axis. For example, pole is at the origin. Okay, and we know that the contour must not pass through a singularity. A singularity is nothing but a pole, because at that point the value of function will be infinity. So we need to skip those singularities. The contour cannot pass through it. So we will assume, now in this example there are 3 poles which are on the imaginary axis. So you need to jump like this, skipping those poles. Okay, and that shape of the jumper is also semicircular, but that semicircle is with very small radius. Radius is considered to be epsilon, which tends to 0. So this is a big semicircle that we have, okay, with radius r, where r tends to infinity, and these 3 are small semicircles with radius epsilon, which tends to 0. And here in this case, please understand the direction is from minus pi by 2 to plus pi by 2, because the contour direction is this. It is going in this way and then it is going up. Okay, so for this direction, the angle direction would be minus pi by 2 to plus pi by 2. Okay. For this section, the angle direction would be plus pi by 2 to minus pi by 2, exactly opposite for smaller portion of the Nyquist contour. Now, if this much is clear, then I'll just brief you about how to solve these problems, and then in the next session we are going to see a solved example. Okay. Now, very first thing that we should do when GSHS is given to us, very first thing that we should be doing is calculate Z and P. You have to look for values, or sorry, poles and zeros of GSHS which lie in the right half of his plane. So those will be Z and P values. Then we need to consider the Nyquist contour depending on the location of poles. Okay. So similar to this diagram which is on the screen right now, we need to consider the Nyquist contour skipping the poles on imaginary axis. There might be 4 poles, there might be only 1 pole, there might be 0 poles, depending on that whether there is a pole or not. You need to use the Nyquist contour, and then you divide that contour into various sections. Okay. So the sections in the previous example also is shown. I'll show in this diagram also. So this might be one section. Okay. Then this might be another section. This small semicircle is another section. Again, this part is one section. Again, a semicircle, this one, and this one, right? Please understand, the Nyquist plot on one side of the real axis is mirror image of the other side, right? So we don't have to actually plot for all the sections. Even if we plot for one section below real axis or above real axis, the another part, its counterpart, will be mirror image. Okay. So for each section, we will have to sketch the polar plot. After sketching the polar plot, we need to check how many times it is encircling the critical point -1 plus j0, and that gives you the value of n. We have already calculated the values of z and p. So if you have z minus p is equal to n, or what we can say, when z is equal to 0, n plus p must be equal to 0. If that is satisfied, then we can say that the system is stable. Now let me tell you, this was the very basic method that was developed. Though it is complex, it is beneficial for commenting on the stability using open loop transfer function, and we can comment on closed loop stability. Similarly, instead of GSHS, if we consider 1 plus GSHS, we will be able to comment on open loop stability as well as closed loop stability, right? So that was advantageous in a way, but it is a complex method, right? So I hope you have understood till this point. If you have any difficulty, you can get back to me. We will end this module here, and in the next module, we will try to solve one example. Please revisit. I suggest you to revisit all the definitions and concepts that we have learned, and please try to put it together, understanding mapping theorem and Nyquist criteria. Okay, thank you.